So now we want to talk about convexity. It's a really important thing, and it's nice to visualize it. And we've learned this through the exercise that we just did. But the first thing is that the estimation error is larger for these longer term bonds and at lower yields. And we can plot the bond's price and yield ratio, and we can actually see and observe this. So at 10% yield, a 8%, if you move from 10% to 8%, you have a corresponding price delta of about $1,400. But if you went from 20% yield to 18%, you have a price delta of about $400. So that is a significant difference. And as you can see, the convexity, the curve is significant. It's not a linear line, as we've already discussed. When you use modified duration, you're actually trying to plot a straight line. So if I'm trying to estimate, let's say, 11%, a shift from 11% here to 10%, you can see here, well, that makes sense that actually it's almost best fit linear line. You could put a linear line there and it wouldn't be that big of a problem. But imagine if you went from 11% to 5%. Suddenly, you can see the linear, if you can imagine a line forming right where my cursor is there, you have a less, you're going to have more estimation error correspondingly, because the straight line is going to have a dramatic delta from the actual curvature line, which is what we want, that takes into account the convexity and relationship of yield and price in a more precise way. So that's quite a huge story. I think this is sort of a helpful visual for it. And we know modified duration is a great shorthand, especially if the leap is minor. But if it's going from, as we've said here, 10 or 11% to 5 or 15 to 5, the error is massive. Now, note though, on this part of the curve, it is almost a straight line, right? So as you get up, your yields go higher, the delta change in price is not so significant. Whereas once you start going into these territories, as you get the yield down to 2%, a 2% change is a massive delta between 12,000 and 16,000. So you're having this very significant characteristic curve, and it's, again, larger as the yields are lower in this curve. So as we've said, the modified duration is a great shorthand, but investors need a measure of interest rate risk that provides a more accurate estimate of price change for larger yield changes, as we've already illustrated. So the way to do this is to adjust our delta price formula using something called convexity adjustment. And this adjustment to the linear price change improves the estimate for price change to reflect the nonlinear nature of the price and yield relationship. So when we look at this, let's look at the actual formulas. So it's actually not as complicated as it already immediately looks when you look at this slide. So let's start up here with estimating dollar change in price. So this isn't that complicated. So we've been doing linear thus far. So if we want to estimate the change, that dollar change in bond prices, which is the exercise we just did, we would basically take modified duration, multiply it by the price, and multiply the change in yield. So we take the modified duration and times it by the price. And so I'll show you here just a second. This is precisely what we did here. We calculated, as you can see, the basis point times our dV of 1, which is our modified duration times the price. If you recall how the dV of 1 is calculated, because the dV of 1 pulls in this information, it calculates it seamlessly this way. This is our linear calculation. So if we were to take the modified duration, so modified duration is here, and if I were to times it by the price, and then times it by the actual change in yield, which is, in this case, 0.2, yes, it'll deliver me 16.871, and that's actually, boom, exactly the same as this calculation. So our formula is reflecting the reality. And this is exactly what we have here, modified duration times price times change in yield. That's exactly what we just did in Excel 5 seconds ago. So with convexity, you just take this formula, the thing we just went through, and we add convexity adjustment, and we're going to define that in a second. So that's all you have to do. You add this substance, this calculation, to derive a better estimate of closer to the actual convexity that Excel can precisely calculate to endless decimal points, by the way. So duration is really about the estimate change in price. So here we're just basically dividing both sides by price. So instead of looking at dollar price, we're actually looking at percentage. And so then you get modified duration and a change in yield. So with convexity, all you have to do is add the convexity adjustment divided by the bond price. So what is this convexity adjustment? That's what we're going to tackle now. How do you calculate this little adjustment that makes these linear adjustments, linear numbers better? So it's not that bad. It's here. So it's bond price plus or bond price negative. So A and B, actually I'm going to, so A and B here, so this formula basically describes it. And convexity equals a price if yield increases by delta Y yield plus a decline in delta yield minus 2 and the corresponding initial price. And then initial price times yield to the delta yield to squared. So this is kind of like, you know, basic math, actually. What we can do with Excel that's really useful is apply this math in a more constructive, robust way, and that's what we're about to do.